is Richard. I'm a software engineer at Anyskill, and this is Travis, who's also going to be talking in the second half of this talk. He's a software engineer at Uber. We'll be talking about Ray and its growing ecosystem of machine learning libraries. So for a quick overview of today's talk, I know a couple of folks tuning in today who haven't heard about Ray. So we'll begin with a quick whirlwind tour. We'll then be overviewing some of the new exciting integrations around Ray's broader machine learning ecosystem. And finally, Travis will be diving into the integration of Ray into Uber's open source machine learning ecosystem. So you'll be seeing the forces joined between Horvath, Ludwig, Ray Toon, and Ray on Dask on Ray. So I want to start with a quick overview of Ray for those who are not familiar. Ray is a project with a mission to simplify distributed computing. So it's a project that we've been working on for the last 4 years, and it's associated with 3 different labs at UC Berkeley. These labs have had a long tradition with open source, and projects that have come out of these labs include Spark, Cafe, Apache Mesos, and now Ray. So Ray itself consists of 2 primary components. The first part is a Ray core, which is a simple framework for distributed computing. We'll be talking about the primitives that Ray core exposes in a later section of this talk. The second primary component is the Ray ecosystem. So there's many libraries that are packaged with Ray for domain-specific utilities, including hyperparameter tuning, reinforcement learning, model serving. So I just want to talk really quickly, where does Ray stand in relationship to the rest of the compute and Python ecosystem? So Ray is very similar to Dask or Celery, if you're familiar with those sort of systems. It's a framework for distributed computing for Python. With respect to the rest of the compute ecosystem, Ray runs on any cloud. So it works with AWS, GCP, Azure, even Kubernetes. And it's also very broadly compatible with other libraries in the Python ecosystem. So this includes NumPy, Pandas, TensorFlow, PyTorch, Spacian, etc. So now that we have some context about Ray, you might be wondering, well, why does Ray exist in the first place? So in order to really understand Ray, we have to first take a look at the history of distributed computing. Now, distributed computing is not new. Almost every decade, a new category of applications went distributed. In the 1980s, we saw the emergence of high-performance computing, or HPC for short. This led to powerful simulators which allowed engineers and researchers to do weather forecasting, molecular modeling, and much more. In the 1990s, we saw the rise of the internet and the web. This led to building highly distributed systems to support popular websites with millions of users. Next, in the 2000s, we saw the emergence of big data. So we had many of these internet companies accumulating large, vast troves of user data to improve the user experience while also improving their own business strategies. And finally, as we enter the 2010s, we're seeing the emergence of deep learning. So companies are starting to leverage this data collected to build powerful feedback systems and models, enabling new applications. And these models are getting larger by the day and are often tied to distributed training capabilities. So as you can see, over the years, more and more workloads became distributed. And what's interesting is that actually, once they became distributed, they remained distributed. So now, after four decades, we have these 4 pre-existing workloads: HPC, big data, microservices, and deep learning. And what we're seeing is that a common trend is that these workloads are starting to become tightly integrated with each other. And this growth and this concentricity is largely due to the growth of machine learning and AI workloads. So for one, many of these artificial intelligence workloads are already overlapping with high performance computing. Distributed training frameworks like Horovod leverage NPI underneath the hood, a system developed by the HPC community in the last 30 years. We're also seeing microservices, which power many of today's web services to start to integrate with machine learning components. This allows applications to better be tailored towards specific users, ultimately improving the utility of these different microservices. Finally, deep learning applications, AI applications, and big data are strongly overlapping. Because many of these AI models and applications today require huge amounts of data to train and become performant. So creating these distributed AI applications is actually quite hard. Despite the convergence of these 4 different workloads, the systems used to support these different workloads are as diverse and as distinct as ever. There's really no single framework built to support these end-to-end distributed applications. So ultimately, the promise of the Ray project is to allow developers to build end-to-end distributed applications that are both general and easy to use. So now that we've motivated Ray, let's quickly talk about the core primitives of Ray, which promise to simplify distributed computing. The Ray API mirrors the way that programming is traditionally done with functions and classes. In Ray, functions are converted into tasks, while classes are converted into actors. I'll elaborate more about this in later slides, but let's first talk about functions to tasks. So here we have a couple simple Python functions. The primitive that Ray exposes here is the ray.remote decorator, which takes in an arbitrary Python function and designates it as a remote function. You can then invoke these remote functions with function name.remote, which immediately returns a feature. This feature is an object reference that represents the result represents the result. In the background, Ray will schedule the function invocation on the cluster or on your machine on a separate thread and execute it. Now, this way, many different functions can run at the same time, and you can also construct different these computation graphs using this API. Now, if you really want to actually get the results of this computation, you can call ray.get, which blocks until all the tasks have finished executing and will retrieve the results. This API, though it's simple, already enables the straightforward parallelization of many Python applications. And you can read more about this in the Ray documentation. So the next thing is Ray actors. So these are essentially remote classes. Again, here's a simple Python class with a method of incrementing a counter, and you can add a remote decorator to convert it into an actor. Then if you instantiate this class with counter.remote or class name.remote, and a worker process that contains this class is created somewhere on the cluster. Each method that creates tasks that are scheduled on that worker process. In this example, we have 2 different tasks, inc.remote, and that's called twice, and they're executed sequentially on that actor. They all share the same state as the same actor, obviously, which is the semantics of a class. And you can also easily access GPUs with the Ray API by simply specifying some resource request. This allows users to easily parallelize their AI applications. So given that what we see here, this is a really powerful API, and now we're seeing a large growth of different libraries using the Ray core framework to distribute and parallelize their workloads. So one area that we've seen enormous growth is with the libraries that we've developed on top of Ray. So there's basically two categories of ecosystem libraries. So the first category is libraries that we develop as part of Ray, these native libraries, and the second half is the third-party libraries that integrate with Ray. Two of the first libraries that we began building as part of Ray were RLib for reinforcement learning and Tune for hyperparameter search. Today, these are some of the most popular libraries for reinforcement learning and hyperparameter search in the world today. More recently, we began working on libraries for model serving, deploying models in production, and distributed training. Now, of course, the most exciting part of this growth is this third-party libraries that are built on top of Ray. So spacing and Hugging Face, which are Hugging Face transformers, which are two of the most popular libraries for NLP, integrate with Ray to train on multiple GPUs and tune/deploy models. You can also scale Horovod, PyTorch, and XGBoost on your Ray cluster and use them with Ray Tune and Ray Serve. So Travis will talk a little bit more about how Uber's open source ecosystem is leveraging this in the second half of this talk. We also see AutoML frameworks such as Ludwig from Uber explore integrations with Ray. And Travis will also will explain about the roadmap for this integration in a couple of minutes. In addition to these training libraries, we're seeing major cloud machine learning platforms such as SageMaker and Azure ML integrate with Ray Tune and RLib for providing training and reinforcement learning services. And the list just goes on. So we see, HyperOpt and Optuna, some of the most popular hyperparameter tuning libraries, integrate with Ray Tune for hyperparameter search. Dask, which is a popular distributed system in Python with a great data frame library, can now be run on top of Ray. We have weights and biases and Selden, which integrate with Ray Tune and also leverage Ray for massively parallel model explainability. And these are just just a small section of the many libraries that are integrating with Ray today. So what we're actually seeing is that Ray is becoming the go-to framework for not only scaling simple Python code, but also scaling Python libraries. The benefit here is not just that you can use one of these libraries, but rather you can use them all together and scale the entire application chained with all these different libraries on a single cluster. So if you're a library developer and you're interested in scaling your library with Ray, do reach out to us on the Ray Slack or on the Ray GitHub. We'd love to help out. So that's it about the Ray ecosystem for where it is today. And Travis will now talk about some new exciting developments for Ray with Uber's open source machine learning stack.
Thanks, Richard. Yeah, so as Richard said, I'm Travis. I'm a software engineer at Uber. I am the maintainer for the Horovod project that does distributed deep learning. And I also am a co-maintainer for the Ludwig project that does AutoML. And today I'm going to tell you a little bit about how we see Ray fitting into both the internal work that we're trying to do at Uber in terms of providing ML infrastructure to our internal data scientists, as well as how we're leveraging Ray and the open source products that we use within Uber and also contribute to externally in order to provide a more seamless experience for our open source community as well. So let's start by talking a little bit about Horovod. So Horovod is a project that was originally developed at Uber. It's a framework to do large-scale distributed training of deep neural networks. Its goal is ultimately to make distributed training fast and easy for any framework and any platform. So we originally open sourced Horovod back in 2018, or at least it became a member of the Linux Foundation in 2018. And since then, one of our primary goals with Horovod has been to figure out ways that we can make it more accessible to people who maybe don't have the kinds of sophisticated high-performance computing clusters that research labs or big companies do. And that's one of the reasons that we're really interested in exploring Ray, because it enables this kind of capability to scale up your compute resources very naturally without having to get involved with a lot of data infrastructure kind of expertise. So Horvath on Ray was a project that started actually just a couple months ago, I think, and Richard actually was able to implement it in, I believe, about 400 lines of code. So it just kind of speaks to the very seamless kind of APIs, or very like reusable APIs that Ray provides to kind of make such an integration possible. And as I'll explain in some of the further slides, being able to run Horvath on top of Ray in isolation is cool unto itself, because a lot of people struggle sometimes with launching a Horvath cluster, being able to train your job, in the cloud, something like that. But what really makes this particularly powerful is how it interacts with other stages within the machine learning workflow process. And to kind of talk a little bit more about that, I want to mention as well, and kind of deep dive as a case study, the Ludwig project. So Ludwig is another open source project that came out of Uber AI. And its goal is to make deep learning kind of an abstraction on top of just the problem space of, I have some inputs, I have some outputs, I want to train a model. So it's effectively an AutoML toolkit for you. So given any inputs and outputs, Ludwig will build the right model for any task. And to do this, we have a very novel architecture that we call encoder, combiner, decoder, where we take your input features, whatever they happen to be, we encode them into a lower level representation, we combine them, and then we decode them into the outputs that you're trying to predict. So Ludwig is a good case study for lots of ML problems at Uber, because when Ludwig started, and this is also true up to this point, it focused fundamentally on the research problem. How do I solve this research problem of being able to predict any attribute I want to predict given any input data I happen to have? And typically in these sorts of scenarios, the researcher will do what's easiest to do for them in their local machine, their local development environment, which is usually something like Pandas. It's a very elegant API for doing data processing. And so we read the data in whatever format it's in, CSV, Parquet, et cetera. We read a very simple YAML file config that defines the steps that you want to, what your features are in your data set, how you want to interpret them as text or categorical data, et cetera. And then we do the pre-processing on the single worker using Pandas and output the result as a set of training data sets as NumPy arrays. So we have a training set as NumPy, validation set, test set, et cetera. In the next stage, we use TensorFlow to actually do the training on these data sets. We output a trained model, and then we similarly run evaluation on the held out test set, and then finally output the results to some kind of storage layer, usually a local file system, something like that. And so this is at the point where the scalability challenges start to creep in, as you say, okay, well, this works very nicely on a single machine. It's very easy to iterate on, very easy to develop. But how am I going to scale this up to process very large data sets? How am I going to run this in production in kind of a retraining scenario, something like that? And this is the kind of situation that we encounter very frequently on the machine learning platform at Uber, is data scientists having this exact scenario, wanting to scale up their pandas and local TensorFlow code to very large scale. So with Ludwig, we have a single worker for pre-processing. We do support Horvath currently for doing training, but single worker for pre-processing. And one of the biggest constraints is that because we're using pandas, the whole data set has to fit in memory. So okay, we definitely have to address that. In terms of other challenges, hyperparameter optimization is a big one. So in our situation, we're not just optimizing over learning rate or something like that, or even the architecture of the model, or even optimizing over the pre-processing steps, so what you might call feature engineering, and trying to find the best total combination that produces the best model. So what this means is that if we want to scale this up, we also have to think about not only how do we scale the training, but how do we scale the pre-processing, and how do we scale that together within the hyperparameter optimization. So conventionally, how you would typically approach this problem, and this is how we approach it at Uber today, is that you would break apart your single worker training script into a series of components that run on specific infrastructure. And this infrastructure is typically heterogeneous. You use a certain piece of infrastructure for one stage and a different piece of infrastructure for another stage. For example, if you're doing a lot of data processing, you almost always are going to be using Apache Spark. It's a very popular framework for doing large-scale horizontal scaling of your data processing workloads. And then once you want to do the training, you would want to use something like Horovod to distribute the TensorFlow process across multiple GPUs and sync the parameters. And then when you do evaluation, because you don't have to sync any state between workers, you might want to switch back to something like Apache Spark again, maybe this time using GPUs to accelerate the inference. So how are you actually going to stitch all these things together? Well, since these are very heavyweight steps, very heavyweight piece of infrastructure, you would typically use some kind of workflow engine like Airflow, Apache Airflow, to define each of the steps that you want to perform and make sure that you spin up the right infrastructure, you have the right sources and sinks for your data, and that you transition with fault tolerance to the next stage. Because these operations are so heavyweight, you need to be prepared for any mishaps that might occur along the way. So after the training step occurs, you write your model to some large intermediate storage like HDFS, something like that. And then because all of this is happening in a fully remote setting, you then might need to have a final deployment step that actually takes the model from the distributed file system and puts it into your model store. So why is this not ideal? Well, I think one of the first challenges that we came across when we were looking at doing this for Ludwig was that we looked at the pre-processing code that we had written in pandas, and we realized that we were going to have to basically do a complete rewrite to make it work with Spark transformers. And so what this effectively means is that we're having to maintain two distinct code paths, one for local or small scale training and one for large scale training. And when we talk about scalability, we really don't want to think of scalability as just tens or 100s of machines to thousands or millions of machines. I mean, that's certainly great, but really the difficulty is in going from one machine to the tens to the hundreds to the thousands of machines. And so that's where something like Ray can make a really big difference. So similarly, these heavyweight steps, this very heavyweight infrastructure that's requiring airflow, that's kind of an inhibitor to getting this laptop to massive scale from making sense, because no one's going to be wanting to run these heavyweight steps with airflow on their local machine as part of their normal development process. And what about hyperparameter optimization? So airflow is really great for defining a static series of steps that you want to perform, but hyperparameter optimization is a dynamic process, difficult to model with static workflow definitions. So you really have to think creatively if you're going to solve this using this traditional ML workflow design. And that's why we started looking at the Ray ecosystem. So one of the great things about Ray is that not only does it simplify the infrastructure component for you, but it also comes with this huge ecosystem or bag of frameworks that you can pick and choose from and find the one that fits your scenario the best. And this is a really powerful thing that I want to mention, because very often, because infrastructure is usually such a heavyweight thing, you're typically locked in. So it's like if your company is invested in Spark, like you got to use Spark for everything, right? And Spark is great, but sometimes you might say, well, maybe for this problem, I want to use Dask. So, with Ludwig, everything's in pandas. It'd be great to use something like Dask or Modin to swap out the pandas data frame for a distributed data frame very seamlessly, right? And that's something that Ray makes very simple to try out. Similarly, Dask is also appealing. It's a pure Python data processing engine, so it's very low overhead when you're debugging. You don't have like Java calls in your call stack. And it has GPU acceleration as a core feature through the Rapids API and QDF. Horovod, as I mentioned before, at Uber, we heavily rely on Horovod to do the heavy lifting and distributed training. It's very fast. It works with TensorFlow, PyTorch, and MXNet, which is important because in Ludwig, we want to maintain framework agnostic code so that, we currently use TensorFlow, but in the future, we also want to be able to support PyTorch. So Horovod makes that very simple. With the Elastic API introduced in version 0.20, we also have fault tolerance and auto scaling out of the box, which can also be run on Ray without any special considerations. And it's very flexible too. So there's no restrictions that Horovod puts on the structure of your training code. Most other frameworks require that you have to kind of restructure your code to make them work with their method of doing distributed training. But with Horovod, you just add a couple of extra lines in your code, wrap your optimizer, and then you're good to go. And finally, Ray, of course, it brings everything together into a single infra layer and also provides several additional frameworks that we can't find any similar alternatives to and that are really great, like the RayTune framework for hyperparameter optimization, RayServe for doing serving. So those kinds of capabilities are not only just provided by Ray for free, but they're also the best in class at what they do. And being able to leverage that is really powerful as well. So what's Ludwig on Ray look like then? So the nice thing about this setup is that from the user's perspective, from the code that we actually write, everything is exactly the same as in the single node scenario for the most part, except that we have an additional abstraction layer where we replace the preprocessing side with Dask, which effectively distributes our pandas code. And we replace the TensorFlow training side with Horovod on Ray, which distributes the training code. And then finally, we can do evaluation similarly with Dask, running separate copies of the model in each worker to do the large scale evaluation. And then finally, we don't have to have any separate deployment step because we can return the model, the trained model directly to the client running on the Ray head node and write it directly to our model storage without any additional overhead. And similarly for RayTune, we can take our entire processing pipeline and scale it up into multiple parallel trials. And because it's all running on a common infrastructure layer, we can even run the Dask distributed preprocessing, the Horovod distributed training within a single trial using the resources available to us from the cluster. And let's talk a little bit about serving. So as I mentioned before, we can deploy our model to a model store or write it to a file system, something like that. And then for our open source users, this is then very simple for them to just take the model that's been written to disk and use the Ludwig API to launch Ray servers on top of their Ray cluster that can serve the model for prediction. So what's next? So this is work in progress that you'll see in the Ludwig v0.4 release. I'm really excited that this work is progressing so quickly and really thankful to the AnyScale folks for all the work they've contributed to us on the Uber side as well. Going forward, there are some other things that are very interesting that Ray enables that I want to briefly touch on. One of them is the fact that when we move from pre-processing to training, there's this additional barrier where we have to materialize the data set to disk so that we can hand it off to the training side. But people often ask, is it possible that we can eliminate this somehow? And with Ray, we actually have, for the first time, a very simple way that we can. So, theoretically, because these Ray workers, for the pre-processing with Dask or Modin, for example, and the Horovod training are all running on the same infrastructure, we can theoretically do things like co-locate them together. We can have the Horovod workers directly access the memory, shared memory of the Dask or Modin workers or the partitions that they're operating on and be able to do the training that way. And so this is something that we're very interested in exploring. And again, it's all possible thanks to the way that Ray is ultimately designed. So that's it for me. Please check us out on GitHub if you're interested in contributing or trying out Horovod or Ludwig. The links are there. The URLs are hopefully very simple, horovod.ai and ludwig.ai. And with that, I'll hand it off to Richard to close us out. Thank you.
So that's it for this presentation on Ray and its growing ecosystem. So this project wouldn't be where it is today without an extremely passionate community, and that's something that we're really grateful for. If you're looking to try out Ray or Horovod or Ludwig, we encourage you to get involved and reach out to us either on Slack. Go ahead and try downloading Ray or Horovod and Ludwig. and just let us know if you have any thoughts or questions. Thanks again for coming to this talk.